Hi. The first thing I want to talk about is something that statisticians refer to as data enhancement. That's a fancy way of saying people read more into data than the data actually implies, especially when data is viewed out of context. Consider the following. On April 29th, in 2009, CNN, a U.S. television network, broadcast the alarming fact that Mexican health officials suspect that the swine flu outbreak has caused more than 159 deaths and roughly 2,500 illnesses. That's pretty scary stuff until you put it into context. So let's ask the question, how many people die not from the swine flu, but from the ordinary garden variety seasonal flu in the U.S.? Do you think it's 100 every year? Or maybe as many as 500? How about 1,000? Maybe 10,000? Maybe 20,000? In fact, it's 36,000. And that 36,000 puts this 159 in a rather different perspective. Here's another interesting example. An often quoted and indeed accurate statistic is that most automobile accidents happen within 10 miles of home. Well, it's true, but so what? Most driving is done within 10 miles of home. And besides, what does home even mean in this context? The statistic is computed, as it happens, using the registration of the vehicle as the home. That suggests that maybe you could reduce the probability of getting into an accident by registering your car in a place where you're never going to be. All right, let's look at a more relevant example. Another thing that you should be wary about is extrapolating from data. It's not always a bad thing. In fact, we spent a lot of time earlier in the term talking about extrapolation. Fundamentally, we used polyfit to fit curves to data and then used it to make predictions about data points we hadn't seen. And that's clearly an example of extrapolation. On the other hand, you may remember that we also showed the flaws in extrapolation when we looked at a spring and showed what happened when we use our fit to extrapolate how the spring might behave beyond its elastic limit. Extrapolation should be done only when you have a sound theoretical justification for doing so. And indeed, I'm always very cautious when I see straight line extrapolations. Let's look at an example. Here's some actual data about the growth of the internet in the United States. And you'll notice for a period of time, it actually grew in what was pretty much a straight line, from 5% to 45%. This was during the period from 1994 to 2000. But let's see what happens if we use this to extrapolate beyond 2000. We'll take these were the data points we looked at earlier, and we'll extrapolate to, well, today, 2012. What do we see? We see that nearly 120% of the people in the U.S. are currently using the internet. It really doesn't seem likely. There's one more statistical fallacy that I want to discuss, and that goes by the name the Texas sharpshooter fallacy. If any of you live in Texas, it did not acquire this name because people in Texas are believed to be particularly vulnerable to fallacies, but it's that there are an awful lot of people with guns in Texas. Okay, imagine that you're driving down a country road in Texas, such as this beautiful road, and you see a barn that has 4 targets painted on it and a bullet hole right in the center of each target. Well, you stop, the owner of the barn comes out, and you tell him you really admire his accuracy. "Yes, sir," says the owner, "I never miss." A few minutes later, his wife comes out and says, "That's true. There ain't a man in the state of Texas who's more accurate with the paintbrush." What does she mean? Well, as it turns out, what the farmer did is he was aiming for the middle of this wall, but in fact, he's a terrible shot, and the shots went all over the place. Didn't worry him. He went out and got his paintbrush, painted a target around each, creating the illusion of being a sharpshooter. Well, you might think this is silly and no one would ever do it in practice, but in fact, it unfortunately happens all the time. A classic of the genre appeared in 2001 in a paper written by researchers at the Royal Cornhill Hospital in Aberdeen. They reported that they had discovered the following astonishing fact. Anorexic women are most likely to have been born in the spring or early summer. Between March and June, there were 13% more than on average, and 30% more in the month of June itself. Well, let's look at that worrisome statistic for women born in June. The team studied 446 women who had been diagnosed as anorexic. If you assumed that they were evenly distributed over the year, that would tell you that the expected number per month is 446 over 12, which is approximately equal to 37. Well, if 30% more were born in June, that would tell us that they must have seen 48 of their women born in June, thereabouts. Well, let's write a small program to see how likely it is that this happened purely by chance. All right, here's the code. June probability. As always with our simulations, we have a number of trials. And we're going to look at the number of times we get 48 or more women born in the month of June. So we'll look at 446 women. We'll choose a random number from 1 to 12. If it's 6, the month of June, we'll increment the number of women born in June by 1. And if at the end of the trial it was at least 48, then we'll increment June 48 by 1. And when we're done, we'll compute the probability as usual by dividing by the number of trials, and then print the result. Let's see what happens if we run it. Come over here, we'll look at the code, and we'll try June prob, say 1,000 trials. Well, it looks like the probability of 48 births in June was a little bit more than 4%. Let's try it again, just to see how consistent it might be. Still a little bit more than 4%. One more time, just for good luck. A little bit less than 4%, but we can assume that if it happened purely by random, the number would be about 4%, and that would say that with more than 95% confidence, they really do have an interesting result. So perhaps these researchers are onto something, or perhaps not. What's wrong with the logic is the following. You have to think about what the initial hypothesis of the experiment was and the details of the experiment. Had they started with the hypothesis that June was a month in which more anorexics were born, then the test I just showed you would have been the appropriate test for looking at the statistical significance of their results. But that's not what they did. What they did is ran an experiment, looked at 446 women, found the month with the most births, which happened to be June, drew a bullseye around it, and then checked the significance. So what they should have done is not tested the probability of having 48 or more births in June, but 48 or more in any month. Let's look at what happens if we run code to do that. Here's the code that does that. Not much more complicated than the code we just looked at. I'm going to check all the months, find the month with the most births, and then ask, does that month have at least 48 births in it? And compute that probability. So now let's try that. We'll go any prob of 1,000. Ooh, that's a lot more than 4%. Try it again. And again, a third time for good luck. Well, here it looks like we're somewhere in the neighborhood of 44%. That really does not pass the statistical significance test. And so we can assume that they really don't have a solid result because, once again, somebody has fallen prey to the Texas sharpshooter fallacy. To reiterate what I said before, the important point here is that the statistical significance of a result depends both upon how the data was derived and how the result was derived. And indeed, in this case, it depended upon the initial hypothesis. The moral is you can't look at the data in isolation without understanding the experiment that generated it. Okay, I could go on and on in this vein. There are just so many entertaining ways to abuse statistics. But by now, you probably got the message. Maybe you got it a long time ago. The message is it's just as easy to lie with numbers as it is to lie with words. When you look at statistics, make sure that you understand what is actually being measured and how those statistically significant results were computed before you jump to any conclusions. Thank you.